So that was a mouthful. Okay, let's continue on. We just talked about hydrocarbon derivatives. Now we're going to get into saturated and unsaturated hydrocarbons. Saturated hydrocarbons are all hydrocarbons or hydrocarbon derivatives which contain single bonds. Single bonds. So be sure to highlight in your personal copy single bonds. Oppositely, unsaturated hydrocarbons is when you have multiple bonds, such as double or triple bonds in the hydrocarbon or hydrocarbon derivative. The terms saturated and unsaturated actually refer to hydrogens. If every possible bond on a carbon has a hydrogen present, then we say that the hydrogens have saturated it. So that's where they get the term from. You don't have to know that, just know saturated, single bonds, unsaturated, double, triple. Let me give you a couple examples. Here is a saturated hydrocarbon, which I'm going to highlight. That's a saturated hydrocarbon. Notice they're all single bonds. Compare that to a unsaturated hydrocarbon, a little bit lower, following the cursor. Notice the double or triple bonds you see in these unsaturated hydrocarbons. So one of these three is incorrect. Which one is it? Which one is it? This one over here is gone. These other two are correct. They are unsaturated because they contain double bonds. So I'll try to roughly highlight where the double bonds are with the cursor. So hard to tell. Sorry, this molecule has a little bit better viewpoint of the triple bonds. Moving down, here are examples of saturated and unsaturated hydrocarbon derivatives. So in this example right here, this is a saturated, notice all single bonds. Make that mnemonic, saturated, all single bonds. Here's another one, saturated derivative, all single bonds. And then here, the very bottom, are unsaturated hydrocarbon derivatives. Notice how they contain an element other than carbon and hydrogen, which is why it's derivative, and they contain multiple bonds, double or triple bonds. This is one of my favorite ones down here. Most people think that it has to be between a carbon and carbon. Technically, it can be between carbon and another element. So anything with multiple bonds is automatically a hydrocarbon derivative. Ring structures are also an example of a unsaturated hydrocarbon. Just take my word for it, but I'm not going to be testing you on ring structures. I could be testing you, however, on any of these other examples here. So moving on. We're moving. Other terminology, alkane and cycloalkanes. Alkanes are straight chain hydrocarbons. So if you notice in these examples here, these are straight chain hydrocarbons. Notice on the bottom, these are circular or cyclic hydrocarbons. So we call these cycloalkanes. If they form a cyclic structure, cycloalkanes. If they're straight-chained or acyclic, then they're regular alkanes. So more terminology you need to know. Whenever we have a structure that's cyclic, then we like to put the word cyclo in front. Hence, this is a cyclopropane. And this one over here is a cyclobutane. You can also have halogenated alkanes. Notice how we're combining the words. Halogenated is any time when we put in a fluorine, chlorine, bromine, or iodine. So fluorine, chlorine, bromine. That's a big bromine. It's got a big Heine for a bromine. Bromine, and this last one, let me see if I can write it a little bit better. Iodine. So halogenated alkanes, here's a nice example. This is technically a halogenated cycloalkane. Now, we're obsessed with sketching these various organic molecules. So here are two ways that we can sketch. We can sketch using the expanded structure, and we can sketch using the condensed structure. Now, there's another way of sketching it using the wedge dash structure. Something I don't have in front of me, so please ignore that comment. The wedge dash structure, let's go back a bit. We're going back. There we go. This is a wedge dash structure. A wedge dash structure. At this point, you don't need to know that. Just know that that exists. What we're going to focus on are these nice 2D structures that you see permeated through the PowerPoint slide. So these are all on a single sheet of paper, and they're on a single plane. So we call these 2D. Those are the easiest to sketch, and you'll be responsible for these. So going forward in time, forward. There we go. Here are two types of 2D structures, expanded and condensed. The expanded, you see all of the carbon and hydrogen bonds. So all of the carbon-hydrogen covalent bonds. The condensed, they're not shown. They're not shown. So in this case, CH4. Here is another example of an expanded structure. You can see all the carbon-hydrogen bonds. Here are examples of the condensed. In the expanded and condensed, whenever we have a hydrocarbon derivative, oftentimes we have available lone pairs. It's a good practice to use lone pairs. Unfortunately, the book and slides are not consistent. But as you're practicing this at home, I'd highly recommend putting in your lone pairs if they do occur, because it'll make it a little bit easier when you memorize future organic reactions. Here's a nice summary again, a lot of redundancy. Condensed structure, and condensed structure. I do want to point out that there are even more ways of writing 2D structures where we get to be really lazy. The skeletal structure, where all of the hydrogens are implied. Please cross this out because I'll never test you on the skeletal structure. And then finally over here we have the line structure. As the class progresses, these are my two absolute favorite ones. And I do ask you to go ahead and make that comment on the slide. The condensed and the line are my two favorite ones. We will use expanded, FYI, but those are the ones you really need to get down for the future stuff. In the condensed structure, again, all of the carbon-hydrogen bonds are implied. In the line structure, all of the carbon and hydrogen atoms themselves are implied. And all you have is this single line. If you go down to the second row, notice the condensed structure. We have 3 carbons. Over here, the carbon and hydrogen atoms are implied. So the N carbon is implied to be a CH3, and the middle carbon is implied to be a CH2. Let's see better examples of these using the ISIS draw. In this example, let's see. Here on top we have the expanded structure where you can see every single atom and bond condensed. All of the carbon and hydrogen bonds are implied. And then down here we have line angle. So again, all of the carbon and hydrogen bonds are implied. And then if I wanted to, I can go ahead and hide them, so all you see is the individual bonds. I'll hide that, and then voila, all of them are implied. The problem is if we removed all of the carbon and hydrogen bonds, then we wouldn't be able to tell where the carbons are at. So instead, what we do is we sketch it at an angle. So we call this the line angle structure. Again, all of the carbon and hydrogen bonds down here are implied, and if I wanted to, I can go ahead and show them all. Yes, I'm playing around and I'm enjoying it. So here you have all the carbon and hydrogen present now. Carbon and hydrogens present now. And then on this one, if I wanted to, I could show all the hydrogens. Okay, so you'll be responsible for drawing the same molecule in both the expanded form and the condensed form, and in the line angle form, and I'll turn it back into line angle right now. Okay. I do want to point out, if you're writing the condensed form, technically we allow a lot of leeway of where you can put it. The program, for example, auto-positions it so you have direct line of sight with the bonds. In reality, you can actually have the hydrogens to the left, to the bottom, to the right. I always have it to the right. Just keep in mind, if you write it how I do, automatically these individual bonds right here are between the carbons. So think of these bonds as going between the carbons, and the carbon-hydrogen bonds are implied. I think I beat that to death. Moving on. Now, it's important to draw the structural isomer and know the name of the structural isomer instead of just the molecular formula. So there's a reason why we're trying to make a big deal about expanded, line, and condensed. If I just gave you the molecular formula in 101, that's okay. But in Chemistry 104, there's different ways that we could connect up the different atoms. And this right here is one way, and we call this one type of structural isomer. And a structural isomer is one type of molecule whose atoms are connected in a unique way. If we were to make a different structural isomer, then we would change the connections. So the one on the left, its common name is alcohol. This is drinking alcohol on the left. This one will give you a nice buzz, and in moderations won't hurt you. The one on the right is dimethyl ether. This one, even in moderation, could kill you. It's also great for cleaning various oils off of mechanical parts. Notice, same molecular formula, but different connections. And nature really likes this because whenever you change the connections, automatically, and please do me a big favor, underline this, the minute you change the connections, you change the physical and chemical properties. Now, again, this is called isomers. We often refer to these as structural isomers because they have the same molecular formula, but different connections. So let's investigate these a little bit more. Here are more examples of structural isomers. Let me give you a layman's definition. Very easy. Molecules with the same molecular formula but different atom connections. So the one on the left and the one on the right, same molecular formula, but they have different connections. Consequently, they also have different names and they have different physical and chemical properties. We can write them as condensed formula, or we can write them as line structures. So this is why we need to know the expanded line and condensed sketch format. So that way we can differentiate between these various structural isomers. Each of these has their own unique name, their own physical and chemical properties. So moving on, again, structural isomers, same molecular formula, different structural formulas. I really should mean it's not so much structural formula as it is molecular formula. So if I were to sit there and change it, really should be molecular formula. So if I have two molecules and they have different connections, then they're structural isomers of each other. So think of molecular formula as good old molecular formula such as C4 or C5H12, as you see here. C5H12. So moving on. Now, one of the big problems of writing a 2 or 3D sketch is we need to keep in mind that each of these carbon and hydrogen bonds, you can think of them as being axles, where if the hydrogen and carbon were wheels, they could rotate. So in this example right here, if this is an axle, then this carbon will rotate around in a circle. And what we found in nature is not only are these molecules moving, but all of the carbon and hydrogen bonds and all of the carbon-carbon bonds are always rotating. And I'm running out of space to write the word rotating, but rotating. That's pretty ugly. But let me touch upon this subject a little bit more. So, highlighting this molecule that I'm doing right here, if I were to sit there and focus on this particular bond, and I'll give you a second to take a look at where my hand is, my virtual hand is anyways. This one right here is rotating. Now I'll take a look at this bond over here. If this is rotating, then it will go around and around and around. Now, all of these bonds are constantly rotating. So that means these are all simultaneously rotating around all at the same time. So, what this means to you is there's more than one way to write the same structural isomer. So, we have a term for writing the structural isomer in different rotations and overall shapes. We call these conformations. A better definition of conformation is it's a snapshot of a moving, rotating molecule. So, there's more than one way that we can sketch a conformation for a particular structural isomer. I want you to take a look at all of these molecules right here. These are all the same molecules. Again, these are all the same molecules. These are all the same structural isomers. They've been written in different rotations. So we can say they're all the same isomers, structural isomers, but they're different conformations of each other. Different conformations or snapshots of each other. So going back to the slide, this creates a lot of problems because there's more than one way of writing a molecule or sketching a molecule. In this case, here we have one conformation. In this case, we have another. So now we need to get into naming. First off, in order to name a molecule, you're going to have to figure out, is it a parent or is it a branch? Is it a parent or a branch? So here are the 10 parent names you have to memorize. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Here is their condensed structural formula. First thing you need to memorize is meth is for 1 carbon, eth is for 2 carbons, prop is for 3 carbons, but is for 4 carbons. The easiest way to memorize this is memorize the number of carbons, then go ahead and draw the skeleton. In this case, ethane is 2 carbons, and then remember the 4-bond rule. If it's not attached to a carbon, then it has to be attached to a hydrogen. So I love the 4-bond rule because I can easily figure out whether a hydrogen is present or not. For example, in ethane, and I'll go ahead and I'll use the highlighter. This carbon right here is only attached to one other carbon. So it has 3 bonds left. So therefore, these last 3 bonds are attached to this hydrogen right here, CH3. Same with this CH3. If we were to sit there and take a look at heptane, for example, and take a look at a middle carbon, and highlighting this right here, this carbon is attached to 2 other carbons. So therefore, obeying the 4-bond rule, there's 2 bonds left which are attached to hydrogens. So you need to memorize these parent names and these structures. Once you have those memorized, then to start us off gently, I want you to memorize 2 sets of branch names. The first one are the alkyl branches. The second one are the halogen branches. Halogen consisting of fluorine, chlorine, bromine, or iodine. Now basically what we do is we cannibalize the parent name and we add the ul, the YL. So if we're adding in a single carbon alkyl branch, then it's a meth-ol. If we're adding in a 2-carbon branch, then it's going to be a eth-ol. So notice they're originally derived from the name methane for 1 carbon, ethane for 2 carbons, but we added in the al. Halogens, when you're adding them as branches, you need to change the name from fluorine to O. So, if fluorine is a branch, it's not fluorine, it's fluoro. If it's iodine, it's iodo. Bromine, bromo, and chlorine is going to be chloro. So, this summarizes what I just mentioned. Methane, if it's going to be a branch, then it's going to add the ul, eth-ol. After that, we need to go ahead and figure out where the branch is located at. So we need to develop a organic zip code. We start from the side which is closest to the branch. So in this case, the carbon to the end carbon